Hello everybody, this is video 6.6. We're going to be looking at decimal division. Um, so yeah, let's get started. So when we started talking about decimal multiplication, one of the things we talked about was the importance of estimation. And I don't want to talk about division only as a function of multiplication, but there's obviously a connection between the two, so it's important to contextualize division in regards to multiplication. So we can look at the problem from section 5.2. We had this problem 2.18 times 5.6, and we did the problem first without any consideration for the decimal point at all, and we got 122.08, so 12,208. And then we talked about where the decimal point would go based on sort of our idea of an estimation. And we know that this is approximately 2, we know this is approximately 5 or even 5.5. And so we know that our answer should be around that 10, 11 range. And so when we looked at this in section 5.2, we sort of agreed, we'll go, well, 1.2 is not nearly enough, and 122 is clearly way too much. And so we can use estimation to figure out the decimal point should probably go here between the twos and get 12 and change. Now, the same idea can be applied to division. So if we were to take this problem and use it in this fact family way, we could look at 12.208 and let's divide that by 5.6. Now, if we were to do this problem totally disregarding the decimal point, so let's get rid of those decimal points. Well, we already know what the answer is because we've seen, this it's the fact family version of this problem over here. So we know the answer is 218. So we can tell what this answer is. Now, so if we put these decimal points back in where they go, so 5.6 going into 12. So now we have to figure out where this decimal point goes in the 218. And now we have to give ourselves a little bit of leeway. I mean, we're estimating. So some of you, most of you, hopefully, already know that when we get done, these decimal points should line up from my dividend with my quotient. So the way we've written this, when we did this as a whole number problem, we're not worried about decimal points at all because everything right justifies and everything's in the right spot. So when we get done with this, it's going to look a little wonky, but it's because we're doing it by estimation, not by following the algorithm. So we know that we got a little bit more than 5, about a little more than 5.5 going into 12. So if you look at this 218, 21 feels a little heavy. I mean, 5 going into 12 is not going to go in 21 times. That's not quite right. We've got the 21.8. We know that's too much. We've got the 0.218. That's not nearly enough. So we get a pretty good sense that it's going to go in about 2 times. 5 goes into 12 2 times and change. So 2.18 makes sense. And so, like I said, this looks a little weird because we know these decimal points should line up. So if it's going to bother you, you can always rewrite it like this, where the decimal points do line up. But the point is about the estimation and using the same idea that we did from multiplication into division. Once we've defined this process, at this point we would have already done the long division algorithm, this scaffold approach. So rather than starting at moving this decimal point, moving this decimal point the same number of places, and then doing the division as normal, this is a great opportunity to talk about estimation. It is an NCTM standard that doesn't get hit quite as often as it should. It's a skill that research shows students really struggle with, and a lot of it is because we focus so much on like the precision of mathematics that we don't always take time to look at the importance of estimation in mathematics. And so it's a great opportunity to do that, and it allows us to show students how to look at their work and really see how possible their answer is. So if a student were to accidentally do this problem this way and have the decimal point here before the 2, so if they were to do this problem and have the decimal point here before the 2, hopefully in the course of our instruction, we get them to look at their answers and ask themselves, like, does that seem like a reasonable answer? Could 5 go into 12 0.2 times? Does that seem reasonable? And hopefully get students to look at that and recognize, no, that's not nearly enough. My decimal point, either my answer is just, completely wrong. I need to start all over, or the decimal point's just in the wrong place, and really assess their work like that. That metacognitive piece, that reflective, introspective piece, is really crucial to mathematics. Okay, so let's look at this problem as an example. 3.76 divided by 2.35. And there's a couple of different ways that we can approach this problem. So I want to do it first by estimation. And then I want to do it the second time by the algorithm, by the sort of generally accepted algorithm. So by my estimation approach, I'm just going to do this problem absolutely disregarding the decimal points. So I'm just going to do 376 divided by 235. So 235 won't go into 3, and it won't go into 37, but it will go into 376. So I can't take any groups of tens or of hundreds, but I can take groups of ones. And there's one group of 235. So I'll subtract that off. I get 141. I can stop and make sure this number is in the right range. It's not negative, clearly, and it's not greater than 235. So there's nothing here that indicates I could take another group of 235. So I know that one time is correct. I'm going to put in my decimal point. I'm going to put in this 0. And so now these 141 units, I'm going to break into 1,410 tenths pieces. And that's what this decimal point does. It now lets us know that we're sort of like refocusing on, we're breaking down, we're regrouping from units, from ones into tenths. So 235 will go into here 6 times. So this is 1410. And so I got a remainder of 0. This divides evenly. Now, I get this answer of 16 up here. Let me fix that 6. I'm making it worse, actually. Now, I can move this decimal point up if I know to do that, or I could just leave this 16 as it is. And it's not going to make that much of a difference, really, because remember, this is an estimation. So I know that my answer is a 16, but I got to figure out where the decimal point goes. And so I'm going to look back at this original problem. And so if 3.76 is being divided by 2.35, does it make sense that it could go in 16 times? Are there, within 3 units, can I take 16 groups of 2 units? Well, that doesn't quite make sense. So we can tell 16 is too big. And if I go to 0.16, this would mean that 2.35 is greater than 3.76, that it doesn't even go in a full time. So I know that's not enough. And so if this is too big and this is too much, we're using the Goldilocks theorem here, then we know that it's 1.6. Okay, so that's our answer. Now, the fact that the solution for 3.76 divided by 2.35 is the same as 235 divided by 376, we're actually going to talk about it on the next slide. So we're going to sort of formalize this in case you're curious about it. But that's not coincidence. I mean, there is a design to that. If we go to the algorithm, the way that you probably learned this and the way that I learned it when I was a child, 235 dividing into 3.76. So we know that this decimal point needs to move as many places as necessary for this to become a whole number, that the divisor becomes a whole number. And so if this moves 2 places, then this moves 2 places. And effectively, I get the same problem before. I get 235 divided into 376. So we're going to move these two places, and then all this work over here just sort of transfers over there. I'm not going to do all the same work all over again. But this is the algorithm. Now, I would put it to you, of these two ways of approaching this problem, which one's going to make more sense? Um, this estimation, at least you can reason through why what is happening is happening. The algorithm presented first, independent of any sort of like rationale, just becomes a series of steps that you do because you're told to do it. Again, it's mathematics by fiat. It's because you're just told and you're just sort of following directions, and that doesn't build mathematical understanding, right? So again, and I've said this a gazillion times in this class already. I'm not anti-algorithm, but I am anti-algorithms that aren't connected to some sort of meaning. So we need a way to make sense of this algorithm. The estimation potentially a little limited because it's not very precise, but it does give us a means to understand how to find an answer. But the algorithm is efficient, but it just needs to be connected to something. So let's take a look at what fuels this algorithm and what makes it work. So if we go back to that problem, the 376 divided by 235, 3.76 divided by 2.35. So one way to make sense of what's going on here is to think about this as fractions. So we know that this is 376 over 100 divided by 235 over 100. And so we know this because we've done expanded form and place value, and we know that the 376 is going to the hundredths place, and so does the 2.35, that's the hundredths place. So we know that these are the fractional equivalents. Now we also know from section 6.1, I believe it was, that a fraction and division are essentially the same thing. So I can write fractions as division, division as fraction. So I'm going to take this division problem here, and I'm going to convert this into what's called a compound fraction. And what that means is I got fractions in my fraction. So I got 376 over 100 all over 235 by 100. And what I would like is for this denominator to not be a fraction. So if I can get this denominator to not be a fraction, then theoretically this is going to make my life somewhat easier. Now, I'll address that idea here shortly. But what I'm going to do to get rid of that, I want to get rid of this denominator, so I'm going to multiply by this denominator as an integer. So if I want to cancel out this 100, I'm just going to multiply by 100 here. But I should know that if I multiply this denominator by 100, I have to keep it balanced, so I multiply this numerator by 100. This is the idea behind whatever you do to the decimal point on the outside, you have to do to the decimal point on the inside. However you adjust the decimal point for your divisor, you must also adjust your dividend decimal point by the same thing. And this is why. Because really what you're doing is you're multiplying by a fraction that is equivalent to 1. And so we know that in order for that fraction to be the multiplicative identity, for it to be a 1, it has to be the same power of 10 in the numerator and the denominator. And so the danger here is that when we talk very loosely and very implicitly about some of these processes, that these fractions that have the same numerator and denominator equal 1, that multiplying by powers of 10s have the effect of moving decimal points. When you start taking these things that don't have any context or don't have any meaning and start chaining them together into an algorithm, you get an algorithm that doesn't have any meaning either. And if the algorithm doesn't have any meaning, then there's really not any way for a student to problem solve, to troubleshoot, to assess what they're doing in that algorithm. But this is why this works. This is why we do what we do in that algorithm. So again, I'll leave this to you. I think it's good for you as future teachers to see, to understand the appropriateness of this for students. I think you have to assess where your students are. this might be something that all your students can certainly see. I mean, you're in a position where you're certainly appropriate to see it. It may be something that you feel like is too rigorous for your class, or maybe something that a handful of students who get really curious about why this works, or have that level of mathematical sophistication can understand sort of what's going on here. This level of rigor isn't for every student, especially at the K6 level, but for those who are ready to see it, I feel pretty strongly that they deserve to see it. So for your checkpoint problem, I'm going to give you a fact here that 552 divided by 12 is 46. So we know that is the case. So given that, I want you to find the solutions to the following problems without doing any calculation, right? So without grabbing a calculator, without doing anything, I just want you to sort of reason through what these solutions would be. So 552 divided by 1.2, 55.2 divided by 1.2, and 5.52 divided by 1.2. So you can see that these are all sort of variations on that first piece. So you should be able to solve all of these without the aid of a calculator, paper, or pencil, and be able to explain how you got that solution, right? So if you have any questions about this problem or any other problem that we've seen so far, by all means, please bring them to class. All right, thank you.